Okay, so today we are going to talk about measuring pulse width and the period of a digital signal. So this is not a lecture, regular lecture. It's a discussion. So since we don't have enough time during lecture times, decided to record the discussion in the video as a pre-recorded video. So let's get started. In summary, what we are going to do today is we are going to measure the pulse width of a digital signal using timer 1 and int0 interrupt. Okay, so int0 interrupt, and you have a couple int0, int1, and int2. So basically, int0 interrupt allows you to use external pin as a source of interrupt, right? So with using int0 interrupt, you can have an interrupt when, let's say, certain pin in your microcontroller changes from high to low or low to high, depending on what you want. So yeah, we will use that, and so we will use timer 1 and int0 interrupt, and we will measure the period of a digital signal again using timer 1 and int0. So a little bit more extensive problem statement about what we're going to do. So we will discuss and write the code to measure the length of a high going pulse, the interval between two high going edge, meaning like the period, right? And we want to know how can we do it in the most efficient way. So if you can kind of two problems here we will try to figure out. So one is, okay, so we start low, or let's say, okay, so then it's gonna the logic state is gonna go high in the pin, and we want to know then it's gonna go back to low again. So we want to know how long high lasted. Okay, so and if you know the period, and if you know how long high lasted, so then we can easily find the duty cycle. So let's say you have a second thing is, let's say you have two such pulses. We want to know the time between the leading edge of the first and the leading edge of the second. So this gives us the period, basically, right? So this, like, the first one gives us the high time, t on time of the signal, and I mean one pulse. And then this gives us the one period, and we are not going to use any display or like LCD display or anything to show the result, so we'll use simulation tool. This is basically what we're going to do. I mean, you have the file, so you can create a new project, and you can use this file here to so you can use this guy in your source file as a source file, and then we will make sure you always set your frequency to 16 megahertz, and then we will compile and run the project, and we will simulate. So we will come to that later. So a very quick review of pulse width modulation. Pulse width modulation is very popular thing, right? And in any kind of control systems, it's pulse width modulation used heavily. It's because it's simple and it's effective, and it's a really neat way of controlling outputs. So like basically what happens is you have a signal, right? So in digital, we have either high or or low, right? So let's say we have 0 volt, or let's say in our microcontrollers we have 3 volt, right? So we don't have anything in between unless we use analog modules, analog to digital converter or digital to analog converter. So we cannot have any voltage in between. But what we can do is we can kind of approximate an analog signal with digital signal. So what that means is, like if this is like a 3 volt, and if this is 0 volt, and during this period, if if signal was on 25% of the time and off, 70%, 75% of the time. So what's the average voltage here? Its average voltage is, average voltage is gonna be 3 volt times 0.25, like 25% of the time, plus 0 volt times 0.75, 75% of the time, over 100%, which is 1, right? So from here we see that like the average voltage for this signal, 70, 70 or 75%, 0.75 or 75%. Oops, sorry, my bad. What I'm doing here, just a second. Yeah, forget about this. Like 0.75 volt. Okay, so average voltage is 0.75 volt. This works. Like if it is a motor, because the voltage changes very quick. I mean, especially like let's say LED and things like that, and motor. Since the digital signal is changing so fast, they are not. It's not gonna be like its motor is not gonna turn on and off like every time signal on and off. So right, so it cannot react that fast. The same thing for LED, right? So if you if you turn on and off the signal very fast, so LED is not going to be able to react that fast, so you'll not see, I mean it's going to react that fast, but as a human eye cannot really see the signal turning on and off that fast, so we will see that it's continuously on. But what's going to change is its brightness is going to change, right? So its brightness is going to change, or in the motor case it's going to be like, because the average voltage over the time is going to be lower, or higher depending on what you want, so the speed is going to be different. So let's say if you have a 50% duty cycle, then the result average voltage is going to be 1.5 volt average voltage, right? If it is if its signal is always on, then it's going to be 3 volt, right? So the average, if signal is always on, then it's going to be 3 volt, obviously. If it is 50% duty cycle, it's going to be 1.5. If it is 25% duty cycle, it's going to be 0.75 volt. So as you can see, these are again average voltages. Like based on these average voltages, the speed of the motor is going to go high or low, depending on the average voltage going high or low. So again, the PWM is basically approximate an analog signal with a digital signal. That's a method to approximate analog signal with a digital signal. I guess that's enough. Sorry if it took a long time. So our microcontroller has 3 external interrupt, okay, where an ISR interrupt service routine can be triggered by a rising edge or a falling edge on a pin. INT0 is hardwired to RB7, right? So here you see RB7 and INT0. So INT0 is hardwired to this pin, so you don't have to use PPS for this. Then we have 2 external interrupts too, like INT1 and INT2. These 2 external interrupts can be routed to pins, peripheral pins RP0 to RP15 using PPS, right? So if this is just enough for you, then that's good. If not, if you need a couple other pins to be used as an external interrupt, then using PPS you can use any of these pins as a source of external interrupt. Okay, so very neat stuff. So you will have the code. You can just stop and look at the code yourself, but I'll just go over the code very quick. Again, the usual stuff. The make instruction cycle frequency is 16 megahertz. That's this line takes care of that. Make all pins digital, not analog. Still, we are not doing anything analog, so that takes care of that. Make RB7 an input pin, right? Because we will use RB7 as external like input, like I mean as an input that creates external interrupt, right? So that's this line takes care of that. So now let's set up the timer. I mean, again, let's standard stuff. First, we turn off the timer, just to just clear everything. Tcon equal to 0, so it clears everything in the timer. And PR1, then we set the PR1 to this value. This is equal to 1 millisecond. Obviously, we did the calculations before, so we reset the timer 1 value, so to make sure we don't have any like a value from previous runs. And finally, after all this setup, we enable the timer. Okay, here we disable the timer, set PR1, clear timer, and turn timer on. And another thing we do is we clear the flag just to make sure we don't have any flag raised from previous runs, and we can set the priority level. This is how you set the priority level. So you have priority level from 0 to 7, right? So the 7 being the highest priority level, and if you have multiple, again, if you have multiple interrupts happening at the same time, which is not common thing, it's really difficult to, if it is really rare to have like 2 interrupts happening at the same time, but still, if things running like for years and very like doing a lot of things, this is gonna happen ultimately, right? So it might not happen in a couple minutes, couple hours, depending on what you are doing, but if it runs very long time and somehow things gonna be overlap, and then this is gonna happen. So in that case you can set the priority level to make sure, if you have multiple interrupts, you can tell, okay, which one should run first. Okay, so default priority level is 4. Like if you don't do anything to this interrupt, like a timer 1 interrupt, it's gonna be 4. So actually this line is really unnecessary, but just to show you how you can change the interrupt priority level for timer 1. So if you want to make it 5, you can go ahead and do that. That's fine. But if you don't do anything, it's going to be 4 anyway. Okay. And then we enable timer 1 interrupt. Just a second, guys. Okay, so sorry, I had to take a call, and yeah, so here we enable the interrupt, and that's all there is. So now at this point we set the timer and everything. So let's move to next line. Here for int0 external interrupt, we can set I'm trying to use this pen here, but okay. So here, this is how we enable the polarity set to the detection of a positive edge. Again, if you find the register in the data sheet, if you find the register for int0, maybe I can show it later. So so this helps us to set the polarity to detection. Do we want to detect positive edge, or do we want to detect the negative edge, or if we want to detect both? So this takes care of that. So we want to detect the positive edge. Again, this is int0 flag. Again, we had another flag. We had the timer flag in the previous slide. Like you have that flag raised when you have overflow, like timer overflows, right? This is different flag. So this is int0 IF is you will have a flag will be raised when you have like edge detected, right? So we want to clear that one too, because again, we don't want to respond to previous event, so we clear that. and then finally we enable the int0 interrupt. Okay, so let's move to the next slide. Again, yeah, that's what I was talking about. So here it is. Here's the external interrupt 0 edge detect polarity bit. So I wanna, correct myself here. So you have two options. You can either detect the rising edge, or you can detect the falling edge. So if you wanna detect rising edge, so you set it to 0, like this pins. int0 EP, you set this pin to 0, and or if you want to falling edge detect it, so you set it to 1 again. So you set this bit to 1. So you cannot have, it looks like you cannot have detection for both at the same time, right? You have to choose either one or the other. Okay. Okay, so then, like in the main, we don't do much. And it's not doing anything relevant to measuring the pulse width, and just counts while the interrupt do the work. So we will do the work inside ISRs, in interrupt functions. So main is just, you don't have to have that count anyway, so you can just leave it empty. But just to see if it is doing something, we just put count plus plus. But we will do the measurements and things like that inside interrupt functions, interrupts, ISRs, sorry. Okay, so here's the approach. Okay, we set the timer. We set the int0 external interrupt peripheral. So we already did that, so it's gonna detect the high edge, right? When RB7 goes high, we will record the timer 1 value, so it's gonna be count 1. So we will have an interrupt. So when this happens, there will be interrupt flag raised. When that interrupt flag raised, we will say, okay, save the timer 1 value to count 1. Okay, and then we will set int0 to detect, we will change it, and we will say, okay, detect the low edge. Okay, and like from going high to low, falling edge, detect the falling edge. In that case, again, we will record, we will have another interrupt for that, and we will detect the falling edge, and we will record the timer that happened, the time value when that happened, to count 2 variable. And pulse width is gonna be count 2 minus count 1. Well, this is true only if timer 1 never overflowed. Okay, so if timer 1, like if between those two, timer 1 is counting up to whatever PR1 value we set, right? So this is gonna be true only if timer 1 never overflowed. Okay, well, that's obviously difficult. I mean, it's almost impossible to promise that. I mean, you can kind of make it happen for different circumstances, and then trying based on what you are trying to do. But this is like not like a bulletproof solution to what we are trying to do. Again, you can, for some certain circumstances, you can make it happen. Okay, so it can be just that simple for you. But if you cannot promise that overflow is not going to happen in timer 1, so we can come up with this approach, right? This algorithm here. If we could guarantee that our pulse width is always less than or equal to timer 1, again, if we could guarantee that our pulse width is always less than or equal to timer 1, then this is what we can do. Okay, again, so we do the same thing. So this part is same. And then here we can say, overflow happens, but um, like you are kind of measuring. So you might have overflow at some point, but then we check, right? So we check it. Okay, we say, okay, if count 2 is bigger than count 1, then pulse width is going to be count 2 minus count 1. Okay, it's that easy, right? Obviously, again, count 1 is the first detection, and count 2 is the second detection. First we detect the high, and then we detect the like we detect from low to high, then we detect from high to low, right? So if this value, this is count 1 and this is count 2, so this point and this point. So if this is higher than, if this value is, and again, we make sure that we guarantee that, just this is important, pulse width is always less than or equal to timer 1. Okay, less than or equal to timer 1. In that case, if this is bigger than this one, we can easily say pulse width is count 2 minus count 1. But if this is smaller than this one, what that means is that means there's a overflow happened somewhere here, okay, anywhere in between this high state, right? So what in that case, what you do is, again, I kind of explained this in another discussion, but so if overflow happened here, so what we say is, okay, what's the overflow when it overflows? PR1 plus 1, right? And then we subtract, this is where overflow happens, overflow, right? OV, sorry. And so we subtract overflow from count 1. That gives us this distance, okay? And then we add count 2, so that gives us the whole distance here, okay? So that's what we are doing here. So subtracting, first we subtract overflow from count 1, that gives us this distance, and then we add count 2, because at this point it starts from 0 and it reaches count 2 at this point, so we add count 2, okay? So that's how can we calculate pulse width. Again, this is true as long as you can guarantee that our pulse width is always less than or equal to timer 1 period. Well, if you cannot guarantee that, if you can't say that, if timer could overflow multiple times, one time, like two times, 5 times, 10 times, anyway, during the pulse, if you are having multiple overflows during to detection, then we change the formula very little, okay? So it's almost same thing. Again, in this case, what we do is we still do, but instead of just having one overflow, now we have multiple overflows. So that's why, let's say if we have 5, so we multiply PR1 plus 1 with 5, we subtract from count 1 and add count 2, okay? So that gives us the overflow, okay? Okay, so I mean that gives us the pulse width. So like let's do a few examples. If start is 200 and end is like this is count 1 and count 2, basically 350, no overflow happened, and cycle is 150, right? So if start so obviously in this case, based on how we set up our PR1 value, right? So we set our PR1 value to be you know, we can go back, but let me check what was our PR1 value. It was 15,999, right? So if this is the case, that means, so there's no overflow happened, and cycle is gonna be, basically. So this is like, here is 200 and this is 350. Obviously, this so obviously this is like basically 150 here. If no overflow happened here. If start is 15,990 and end is 300, one overflow happened. And if we didn't have, like basically, if this is the case, so in the first problem, this was the case, okay? So start is 200 and it's 350, no overflow happened. So based on that, cycle is 150, obviously, right? So it says no overflow happened. In the second case, this is the count 1 value start, this is the count 2 value end, and one overflow happened, okay? In that case, if you just say end minus start, of course you're gonna get the wrong value. So what you have to do, you have to apply the formula. Just say, the end value minus start value plus overflow times 1. Okay, and again, if you can rearrange this and have this one, which yields the expected answer of 310. Okay, so because basically what happened here is, again, I'm just talking about this one. So at this point it's 15,990 and overflow happened here. Again, overflow happens 15,999 plus 1 because our PR1 value was 15,999. So, and then ends here is 300, right? So we know this value, so we know the start value, so the difference gives us this, like a PR1 plus 1 minus start gives us here this value, which is 10, like 16,000 minus 15,990, and then at this point timer 1 resets. So, and this is the end, right? So, and like from 0 to end, which is 300. So if you add these two, you get 310. Okay, so let's move on. I hope that this was clear. You can just stop the video and try to understand yourself. Well, we can remove the variable, one variable, by resetting the timer 1 count to 0 when we see the rising edge. So like basically in this formula we can just say, like timer 1 value is something here, right? So if we kind of reset as we detect the rising edge, if we just clear the timer 1 value here, instead of, like let's say here 990, and then it's just continues to counting up to the overflow value, right? 15,999. So instead of like just keep timer keep continuing timing, like counting, so we can just say, okay, I will just clear the timer at this point and I will have 0 here, that's what, that way I kind of get rid of one variable. So I mean, I kind of get rid of the start time because start is going to be 0. Okay, the count 1 is going to be 0. So so what's the, again, that's just this is kind of the algorithm for that. Set int0 to watch low to high. Okay, again, same thing. When RB7 goes high, reset timer 1 count, just clear it to make it 0, and reset the number of overflows, obviously, okay, and set int0 to watch high to low, basically falling edge. And when RB goes low, record timer 1 value, which is count 2. Okay, so in this case, you don't have to say PR like a minus count 1, because again, count 1 is 0, because at that time you reset the timer, count 1 is timer 1 value at that point is going to be 0. So you can just get rid of one variable. You know, it's not a big deal, but that makes things simpler, so you can do that if you want. So again, in the main function, there was nothing in the main. It was just counting up. There was nothing going on there. So let's look at multiple versions of ISRs. So first, we have the volatile unsigned int overflow variable. And it's shared between ISR, and then we have pulse width, same again, volatile unsigned long int pulse width variable. So first here we have like an interrupt for the timer. So basically what we have here, so whenever overflow happens in the timer, so first we clear the flag. This is the must, right? So otherwise it's just gonna, if you don't clear this one, the interrupt is gonna be called again and again, because like a hardware is gonna just assume that you have constantly an interrupt, right? Because you are not clearing the flag. So this is the must. You always don't forget this. Usually when you're debugging, you can spend hours and try to fix the problem, and it might be because of this. So you gotta always, inside when you have interrupt, first thing you want to do, clear the flag that causes that interrupt. Okay. Then basically what this timer like an ISR does is we want to count number of overflows. That's why it's just overflow plus plus. That interrupt ISR is basically only thing it's doing is counting the overflows. It's going to be very helpful. And the second interrupt is due to int0. Again, this is the format, like this is the whole line. Again, first we clear the flag that caused that interrupt. So that's this is must. You gotta have this here. And second thing is I was waiting for a rising edge. So if you have a rising edge, then it clears the timer. That's what we said, right? So like if you want to get rid of one variable, so you can clear the timer and clear the overflow at that point, right? So whenever we have this, so we want to clear the timer value. Again, you don't have to do this. If you don't do this, you use the previous formulas that has count 1 included in the formula. But if you clear the timer at this point, so when you have an interrupt, like external interrupt, so if you clear the timer value, then you get rid of that count 1 variable. And at this point, we want to clear the overflow because we want to count the number of overflows happens, if any, during this time, right? So else is basically else the pulse width is timer 1 plus, timer 1 again. This is the count 2 in a sense, okay, right? Count 2 variable in the when we explain the stuff, because if you have interrupts at some point, let's say this is the last overflow you have, so from here to here is going to be from the last overflow to the final overflow to the end, like when you see the rising, detect the rising low falling edge, this is going to be timer 1 value, because at this point it's 0, and then timer 1 value is going to be your count to. Okay, and then you know, if you have one or more overflows, then you have to multiply 16,000 with overflow. Okay, that's that. And then finally, what we do here is we toggle the, you know, INT0 EP. This was, again, what this was doing is if you set it to 0, it was detecting the rising edge, and if you set it to 1, it was detecting the falling edge. So again, if you can go back and see the register in one of the slides. So this way we are basically toggling it, right? So, you know, like first, if you detect the rising edge, now you have to detect the falling edge. This line takes care of that, because if it was 1, the new INT0 EP is going to be 0. If it was 0, it was going to be 1, right? So it helps us to toggle this, you know, variable. Okay, and when you have falling edge, it's going to be next. It's going to detect the rising edge and so forth. Okay. Okay, let me stop here. So one important thing is when you do, you saw L, like in the formulas, you saw L. I didn't mention about that, but that's kind of important to you know that by default for our microcontroller compiler, the integer constants are treated as 16-bit integer. Okay, if a 16-bit integer is multiplied with 16-bit integer, the result will be 16-bit integer. Okay, even if you make like a, you know, define this x as a long int, so if you multiply these two, result is going to be this, which is wrong, right? Obviously 14,465, right? Because it top 16-bit is discarded. Okay, adding L declares that constant as a 32-bit. Okay, so this constant is 32-bit constant. So in that case, you get 80,000, which is the right value. Again, if you can just try something with one of the code, and you can see the, you know, result x value. Just grab one of your codes that you have this, and, you know, like go simulate and, you know, simulate it and see that, you know, like like you step into and go to that instruction and in that line, and you can see the variable. If you don't have this L there, so it's gonna be, you're gonna get the wrong result. Just important. Or another way of doing it, you can you explicitly cast the constant. So like you can say pulse width, like let's say here, pulse width equal to timer 1 plus long int. Yeah, you can either say long int 16,000 or 16,000 L. So this is another way. Okay, either way works. Version 2, ISR version 2, like this is to measure the period. Okay, again, so whenever we have a timer interrupt, we, you know, overflow increments here. There is no change here. For the period, you know, so period is gonna be, you know, timer 1. Yeah, it's that's kind of very similar. There's not much difference. So this is another version for you know, for INT0 interrupt. Okay, let's move on. So now we're gonna simulate. So you can at this point, if you created your project, so then you can simulate and just following the steps. I'm just gonna do it myself, and you know, this is just a PowerPoint, but I'll record that part as separate and add it to this video. Again, these are the steps. Just follow these steps. Add breakpoints in 2 ISRs where the interrupt flags are reset to 0. So not the beginning of the interrupt line. I mean, just when the line that resets the flag. Just put I started like the breakpoint there. Add, like, we want to watch these variables, so add watches to overflow, number cycles, and timer 1. Then set up stimulus to trigger the int0 interrupt. So I'll do it in the video, so if you can't do it, you can watch that part from the video. And then go to stimulus. How we do this? You go to stimulus from the Windows tab on the top, simulator, stimulus. We did a couple times at this point in other lectures. Use the asynchronous tab, add int0 to pin, and set high as the action. Okay. Add second row with int0 and as the pin, and set low as the action. Okay. So add a third row with int0 pin, and here you say pulse high as the action. Okay, and 50,000 cycles as the duration. Okay, so let's move on. So now we're gonna, at this point, you simulate your code. Again, I'm just gonna do this with the MPLAB X.